Welcome to Lecture 16, in which we will talk even a little more about entangled and unentangled states, and we will also begin to discuss Chapter 5. Here I have pasted on the left-hand side of this page the problem that appeared at the end of Test 14. The format is not great here, but I think you can still follow what's going on. So just to help you read it, it says, suppose that C is a 2-qubit state. It is known that if Alice measures the first qubit of C using the standard basis, and Bob measures the second using the standard basis, the probability that Alice obtains the 0 ket is 0.6, and the probability that Bob obtains the 1 ket is 0.3. And then the question is, if C is measured using the basis 0, 0, 0, 1, 1, 0, 1, 1, when could one say with certainty that the probability of obtaining 1, 0 is 0.28? And the possible choices were A, never, B, always, C, when C is when C is an entangled state, and D, when C is an unentangled state. And this question seemed to cause a little bit more hesitation than usual, so I thought it would be worthwhile for us to look at this whole question in a little more detail. So I'll first say the following. We can always write a 2-qubit state C as A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. And if we if we define two events, if we say let A equal the event that Alice measures zero, and B is the event that Bob measures 1. Notice that these definitions of A and B would imply that A prime, the complement of A, is the event that Alice does not measure 0. And of course, the only two things she can measure, she's using, remember, Alice and Bob are both using the standard basis. So if Alice does not measure 0, it means she must measure 1. And similarly, B prime is equal to the event that Bob measures 0, because it's the complement of the event B, which is the event that Bob measures a 1, and so if he doesn't measure 1, he must measure a 0. So if we define the events A and B in this way and have the resulting definitions of A prime and B prime, then it is always true that the probability of A and B, I'll use the upside down U here that you see. The upside down U is the sign for an intersection when we have set theory, and this will mean that we have both A and B happening. The probability of A and B in this case, now remember, A is the event that Alice measures a 0, and B is the event that Bob measures a 1. And so the probability of both of those happening is the magnitude of B squared. Similarly, the probability, if we had instead wanted to calculate some other pair of events, say perhaps A and B prime, well, that's the probability that both measure 0, and that would be the magnitude of A squared, or the probability of A prime and B. That's the probability that both measure 1, and the probability of that would be D squared. And finally, the probability of A prime and B prime, which is the probability that Alice measures 1 and Bob measures 0, is the magnitude of C squared. So all of this is always true. But this information would help you with some of the questions, some of the other questions on test 14. But let's continue with this. Well, let's ask ourselves how this information relates to what's given in this problem in 14.5. Okay, so we'll say, how does this relate to the question 14.5? Well, we're told in this question that the probability that Alice obtains 0 is 0.6. Okay? So we're told that the probability that Alice obtains 0, and that is the event A, so we're told P of A equals 0.6. And we're also told that the probability that Bob obtains 1 is 0.3, and that's the event we've called B. So P of B equals 0.3. Okay? And so then our question concerns the probability of obtaining 1, 0. 1 in the first qubit and 0 in the second. So we are asked for P of A prime and B prime. Okay, so how does all of this fit together? Well, the fact that P of A equals 0.6, well, that implies, now remember, A is the event that Alice measures 0, and Alice measures 0 in these first two cases. So that implies that the magnitude of A squared plus the magnitude of B squared is equal to 0.6. And likewise, P of B equals 0.3 implies that now remember, B is the event that Bob measures a 1, and Bob measures a 1, the second cubit is 1 in this case and in this case. So that tells us the magnitude of B squared plus the magnitude of D squared is equal to 0.3. Now we also know a little bit more than this. Since well, maybe I'll put it this way: the probability that A is 0.6 also implies that the probability of A prime is 0.4, which implies that the magnitude of C squared plus the magnitude of D squared is equal to 0.4. And similarly, the probability that the probability of B equals 0.3 implies probability of B prime equals 0.7, which means that magnitude of A squared plus magnitude of C squared is equal to 0.7. But we are asked for P of A prime and B prime. Now P of A prime and B prime, as we have already identified up here, that is the magnitude of C squared. And the question is whether or not we can deduce from this information what the magnitude of C squared is. And as you found, as a number of people found, without considering some additional information, this is impossible to do. It's impossible for you to say exactly what the magnitude of C squared is just from the information that's given over here. We want, we're hoping for some additional information. Now, the problem says, when could one say with certainty that the probability is 0.28? Now, so let's ask the question, why would we suspect that the probability of A prime and B prime equals 0.28? Well, the answer is this: if the probability of A prime and B prime is equal to the probability of A prime times the probability of B prime, well, We've already said over here at the right that the probability of A prime is 0.4. The probability of B prime is 0.7. And so then we would get 0.28. But when, or let's say, under what conditions can we say that the probability of A prime and B prime is equal to the probability of A prime multiplied by the probability of B prime? Now, think about this. In elementary probability theory, let's say that you're thinking about tossing, let's say, two coins. Let's say you have a penny and a nickel, and both of them are fair coins. The penny is a fair penny, by which I mean that the probability of obtaining a head on the penny is 1/2. The probability of obtaining a tail on the penny is 1/2. Likewise, the nickel is a fair nickel. Both probabilities are 1/2 there as well. And so if I ask you what is the probability of, if I toss the penny and the nickel, what is the probability that both will end up heads, you would say 1/4, because the probability that the penny comes up heads is 1/2, and the probability that the nickel comes up 1/2, and you would multiply those probabilities and say that the probability would be 1/4. The probability that the penny would be heads and the nickel would be tails would be 1/4. The probability that the penny would be tails and the nickel would be heads would be 1/4, and the probability that both would be tails would be 1/4. Those are the answers you would give, because you would be assuming that I'm talking about a penny and a nickel that are independent of each other. But if instead the penny and the nickel were attached together, so that in some way, so that when heads came up on the penny, you would also get the nickel would also come up heads, or when tails comes up on the penny, then tails would also come up on the nickel, then that would completely influence your answers. Then the probability of heads and heads would be 1/2. The probability of tails and tails would be 1/2, but the probability of heads and tails would be 0, and the probability of tails and heads would be 0. So the assumption here that the probability that both events will happen is simply equal to the product of the probabilities of the independent events, that assumption is good only when the events are independent. So we can say this assumption is valid only when the events are independent. And now we ask, how does this relate to the idea of entanglement? Well, again, C is equal to A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. Now, if we factor out the first qubit, as we've done a number of times before, we would have the following. And now we know that if we want to turn each one of those parenthetical expressions into a state, we need to normalize each one. So in other words, we would divide this parenthetical expression by the square root of the norm of a squared plus the norm of b squared, and divide this one by the square root of the norm of c squared plus the norm of d squared. But in doing that, we don't want to change the value of our expressions, so we need to pull terms out as well. So what we would get is the square root of the norm of a squared plus the norm of b squared times 0 times a0 plus b1 over the square root of the norm of a squared plus the norm of b squared. And you notice that this term here is a normalized state now. It is a valid state because it is normalized. And similarly, for the second term, we would have the following. And as we have said before, now when we factor everything in this way, we say that the probability that Alice will measure a 0 is simply this squared. The probability that she will measure a 1 is simply this squared. The probability that Bob will measure a 0, given that Alice measures a 0, is a over square root of magnitude of a squared plus magnitude of b squared, quantity squared, and so on. Now, again, this expression here is good for any C. But what allows us to say that this is unentangled? Well, you might be tempted to say that it is unentangled if this fraction is equal to this fraction, because then we could factor that out and write this as the product of these terms involving the first cubit and these terms involving the second cubit. And indeed, that would be sufficient. If this fraction here, if this fraction is equal to this fraction, then indeed the state is unentangled. But that's a little too strong of a condition. We don't have to require quite that much. And let me show you what we do want to require instead. Let's write down this expression in just a slightly different form. We'll have square root of the magnitude of a squared plus the magnitude of b squared, 0, and then we have a0 plus b1 over the square root of the magnitude of a squared plus the magnitude of b squared, plus, and now we'll have this small change. I'm going to say e to the I, to the minus I theta times the square root of the magnitude of c squared plus the magnitude of d squared times 1 times e to the I theta c 0 plus e to the I theta d 1 over the square root of, and now notice that if we take the magnitude of this thing in the top, we'll get e to the I theta c multiplied by e to the minus I theta c conjugate, and then e to the I theta d multiplied by e to the minus I theta d conjugate. So we just get magnitude of c squared plus magnitude of d squared. And so if we rewrite this second term in this slightly more general form, all we've done is to multiply it by 1 in the form of e to the minus I theta times e to the I theta. And notice that the e to the I theta there is distributed over both terms. Then we get our most general condition for this to be unentangled is A 0 plus B 1 over the square root of the magnitude of A squared plus the magnitude of B squared is equal to e to the I theta c 0 plus e to the I theta d 1 over the square root of magnitude of c squared plus magnitude of d squared. So in other words, C is unentangled implies if we take the magnitude of the terms on each side multiplying the zero cat, we get magnitude of A squared over magnitude of A squared plus magnitude of B squared well what I was about to say there's nothing wrong with it, but it's just not the direction I want to go in. So let me erase this. And we'll simply circle this condition. This, again, if the state is unentangled, then this condition that we have just circled here must be true. Now, I want to label this last expression for C. I'll label that equation as star. And now I want to start over with the initial expression for C and derive another way of writing it. And this time I won't show all the steps because I believe that it's clear. What I'm going to do now, instead of factoring out the first qubit, I'm going to factor out the second one. So in other words, I'll show just the beginning step here. I'll have A0 plus C1 0 plus B0 plus D1 1. So you can see here I have grouped the terms according to what the second qubit is rather than according to what the first qubit is. And then proceeding just as we did above, we see that this can be written as follows. And I'll label this expression star star. Oh, and actually, let me do one more thing. I'm going to multiply this second term here to get a completely general expression, just like star above is general. We have the e to the minus I theta and e to the I theta. So I want to do the same thing here. We'll say e to the I alpha, and same thing for the d term, e to the I alpha d1, and then we need to multiply by e to the minus I alpha here to maintain equality. Okay, and so then we could find a second general condition for unentanglement. But let's now look at these two expressions, and I want to point out some interesting features that will help us to come to a useful result. Okay, so if we look at equation star, and first of all, let me say, if C is unentangled, then what can we say? Well, the first equation star would imply that the probability of A, remember that's the probability that Alice measures 0. Well, we go up to equation star, and equation this equation star implies that the probability that Alice measures 0 is simply magnitude of a squared plus the magnitude of b squared. But equation star star done here implies that the, let's see now, let me make sure I'm going about this in the right way. Yes, okay. Now again, star star. Here the probability that Alice measures 0, well, it depends on which one of these terms you get, you look at. For instance, if we go with this term right here, remember this 0 here corresponds to Bob measuring 0, and this 1 corresponds to Bob measuring 1. But remember now that if C is unentangled, then this term is equal to this term right here. And so what we conclude from the second one is that the probability of A is equal to A, the magnitude of A, over the magnitude of A squared plus the magnitude of C squared. And we also conclude, by looking at the second term, that the probability of A is likewise equal to the magnitude of B squared over the magnitude of B squared plus the magnitude of D squared. So now if we combine these equations, we get that the magnitude of A squared plus the magnitude of B squared, that's the expression that we get for the probability of A from star. Well, that must be equal to the magnitude of A over the magnitude of A squared plus the magnitude of C squared, but also the magnitude of A squared plus the magnitude of B squared is equal to, let's see, this should be magnitude of A squared here. This is coming, remember, from this term right here. So we have magnitude of A squared over that squared. So there. But also this P of A is equal to this second term. So it's equal to magnitude of B squared over magnitude of B squared plus magnitude of D squared. And now doing a little bit of algebra on that. That tells us that magnitude of A squared is equal to magnitude of A squared plus magnitude of B squared times the magnitude of A squared plus the magnitude of C squared. And for this one, the magnitude of B squared is equal to the magnitude of A squared plus the magnitude of B squared times the magnitude of B squared plus the magnitude of D squared. And for right now, I'll just circle these two equations. We'll come back to them in just a moment. Now, once again, remember that this expression came from star, and this equation came from star star. And now, let's look at both equations again under the assumption that C is unentangled. Let's make a couple of other observations. Let's now look at each one of the equations for the probability of A prime, which means the probability that Alice does not measure 0, which of course means the probability that Alice measures a 1. Well, if we go to the equation star, we see that the probability that Alice measures a 1 is this entire term here, e to the minus theta times the square root of the magnitude of c squared plus magnitude of d squared, is that entire term times its complex conjugate. So the e to the minus theta, I theta, e to the positive I theta go out, and we're just left with magnitude of c squared plus magnitude of d squared. And on the other hand, if we look at star star, which is right here, and look at the probability that Alice measures 1. And again, remember now, this, we should get the same answer whether we look at this or this, assuming that C is unentangled. So if we look at this expression for the probability that Alice measures 1, we would get magnitude of C squared over the magnitude of A squared plus the magnitude of C squared. And on the other hand, if we look over here at the second term for the probability that Allison measures 1, then we would get, we squared the bottom, so in the bottom we get magnitude of b squared plus magnitude of d squared, and at the top we multiply by complex conjugate, and so we get e to the I alpha times d times e to the minus I alpha times d conjugate, so d conjugate, or magnitude of d squared over magnitude of b squared plus magnitude of d squared. Now, as we did before, now we will equate these terms, and so now we come up with a conclusion that magnitude of c squared plus magnitude of d squared is equal to magnitude of c squared over magnitude of a squared plus magnitude of c squared. And likewise, the magnitude of c squared plus the magnitude of d squared is equal to the magnitude of d squared over the magnitude of b squared plus the magnitude of d squared. And once again, now let's rewrite those two expressions. And so we get, so the magnitude of c squared is equal to magnitude of c squared plus magnitude of d squared times the magnitude of a squared plus the magnitude of c squared, and down the last one becomes magnitude of d squared equals magnitude of c squared plus magnitude of d squared times the magnitude of b squared plus magnitude of d squared. And we'll circle this. But now we ask, well, what's the significance of this? Well, if we scroll up to what we had before, here we have P of A, P of B, P of A prime, P of B prime. If we notice that this is P of A and B, P of A prime and B, P of A and B prime, P of A prime and B prime. If we make all these substitutions below, let's see what we get. Okay, so for the first one, we have magnitude of A squared. When we look above, magnitude of A squared is the P of A and B prime. So this is P of A and B prime. Now, what about magnitude of A squared plus magnitude of B squared? Well, scrolling up, magnitude of A squared plus magnitude of B squared, that's P of A. So we come down here, P of A. And what about magnitude of A squared plus magnitude of C squared? Scroll up. Magnitude of A squared plus magnitude of C squared, that's P of B. P of B prime. Here, P of B prime is magnitude of A squared plus magnitude of C squared. So we substitute that in right here. So we have found, simply from the assumption that C prime is unentangled, we come up with P of A and B prime equals P of A, P of B prime. And what about this second one? Well, magnitude of B squared is the probability of A and B. So this is probability of A and B. Maybe I should modify this loop. So magnitude of B squared is P of A and B. Now, as we already found when we looked at this one, magnitude of A squared plus magnitude of B squared is P of A. So, likewise, this magnitude of A squared plus magnitude of B squared is P of A. And what about magnitude of B squared plus magnitude of D squared? Well, if we look up, magnitude of B squared plus magnitude of D squared is right here, and that's P of B. So down here, P of B. Now coming down to our second pair of equations, the magnitude of C squared. Magnitude of C squared is right here. That's P of A prime and B prime. P of A prime and B prime. And that's equal to magnitude of C squared plus magnitude of D squared, which is magnitude of C squared plus magnitude of D squared is P of A prime. So we have P of A prime, and then magnitude of A squared plus magnitude of C squared right here. Well, we've already seen that up here, and that's P of B prime. And then finally, for the magnitude of D squared, if we look above, magnitude of D squared is P of A prime and B. P of A prime and B. and that's equal to magnitude of c squared plus magnitude of d squared, which we just saw over here is p of a prime. And magnitude of b squared plus magnitude of d squared, we saw up here that's p of b. And now, if you look, we just summarize. So, the assumption that C is unentangled leads to the conclusions P of A and B prime equals P of A, P of B prime, P of A and B equals P of A, P of B, P of A prime and B prime equals P of A prime, P of B prime, and finally P of A prime and B equals P of A prime, P of B. So in every possible case, we conclude that the probability of one event, one of these events, and the other one is simply equal to the product of the probabilities of the separate ones. And so therefore, so the assumption that C is unentangled means that Alice's measurement is independent of Bob's. And therefore, when we return to the question, we can see that, as was demonstrated, we can indeed say that the probability of obtaining 1, 0 is 0.28. We can indeed say that when C is an unentangled state. D is certainly correct. And if D is correct, now the only question remains, is anything else correct? If D is correct, certainly A is not correct. And so B and C I will leave to you, and I think that the questions that we'll ask at the end of this lecture will help you to understand those. But I hope that all of this helps you to understand the relationships a little bit better, to understand what entanglement implies, and what unentanglement implies. And I think it might be useful to think of that idea that the example that was given. Think of the penny and the nickel being tossed simultaneously. If the penny and the nickel have no connection between them, then this can be thought of as like an unentangled state. But if there's some spring or other rigid connection between them, then where the outcome of one influences the outcome of the other, this is like an entangled state. So now let's end up this lecture. I think that the title of the lecture here said included Chapter 5, but it looks like we won't be able to include anything about Chapter 5. We will begin that on Lecture 17. But let's now look at some problems for this material. Okay, so now for the problems for this lecture. We're going to, now there will be some more problems in class, but for the take-home problems, they're all related to this same setup. We'll say we have the state 0.6 times 0, 0, plus 0 times 0, 1, plus, I'm sorry, let me start over. We have C equals square root of 0.6 times 0, 0, plus 0 times 0, 1, plus square root of 0.1 times 1, 0, plus square root of 0.3 times 1, 1. And we will let the events A and B be as described above. In other words, A is the event that Alice and Bob are both measuring with the standard basis. Alice is measuring the first cubit, Bob is measuring the second cubit. A is the event that Alice measures 0 for the first cubit. B is the event that Bob measures 1 for the second cubit. And so if this is the state, then I ask, what is P of A? And the choices are A is 0.6, B is 0, C is 0.1, and D is 0.3. And those are the choices actually for all three of the problems, 17.1, 17.2, and 17.3. So 17.1, the question is, what is P of A? 17.2, what is P of B? And finally, 17.3, what is the probability of A prime and B prime? Now that's the event then. A prime is the event that Alice measures a 1. B prime is the event that Bob measures a 0. So what's the probability of that? And again, the choices are the same. And then the final in-class problem is this state entangled or unentangled? So I think that these problems will be fairly straightforward for you, and then we'll have some others fairly similar to that in class. So good luck.